Hello there, welcome to our laboratory. We're going to delve in the fascinating world of metallurgies. And basically, today we are going to explore the transformation effects of heating treatment on aluminum. In this case, we're going to cut little samples of this can. In this case, aluminum can is made for Coca-Cola. And we're exploring the treatment and effects of heat that actually we're going to take. So in the first time, we're going to see this reference that it's not going to happen anything. And in the second place, we're going to take this one of these cans, and we are going to heat it. Like both of these, we're going to heat it, and one of them we're going to put it immediately in a cold sample of water. So we're going to see what's going on. As we commented before, we are going to heat a little bit this one and this one, both of them, and one of them we are going to take it and put it immediately in cold water. Actually, here you can see the process that we are taking. As we can see here is only left 1 minute, and we can see a little bit how it's going on here, and we are going to take these ones into cold water. So there you are, we're going to take this one in the cold water immediately to watch what's going on. As we can see, it's almost there. We're going to take it a little outside, and we're going to take something sharpie to see what's going on here in the reference, the tempering, and the annealing. After taking this with a little sharpie object, in this case the knife, we can see here like a little specks. Like for example, the needling didn't get a hole at all, and this here the tempering is taking like a hole, and here this reference it's not going to happen anything. That actually there's not a hole, but it's actually a mark. In the reference sample, we can see that this aluminum can undergoes a special thermal treatment, and actually aluminum is its initial state has a crystal structure typical of metals that actually we can see here in the reflect, with atoms arranged in a regular pattern. This initial state is what's not considered in the needle structure, so it's not going to happen anything. So here in the hidden sample, when we saw it in the first time, we can see that if you attempt to make a hole in the aluminum can that has only been heated, you might find the metal is slightly softened to the heating process that we can find here. This softening occurs because heating allows the aluminum atoms to move more freely, making the metal more malleable. Like here, it's more malleable, it's like more softened, like you can take it here and it's more easier than this one. And you can see this is like a little more scratching. And as you apply pressure with this sharp object, you might notice here that the metal deforms more easily than when it was in the initial stage. This information actually we can be a result in the metal being of a stretching rather the treatment cleanly. And actually I have like a little hypothesis here, and it's actually because this lead on increase the atom mobility, which can cause dislocation in the crystal structure to move and is clustered. And as we know, this process known as recrystallization might result in more uniform and less defective crystalline structures, which could make the can more malleable as we can expect, and less resistance because we made a hole, and as difference of this reference it's hard one. And here with the annealing, the one with heating and with trying to quenching some like really faster. In contrast of the reference and in the tempering, if you try to make a hole in the aluminum, as I commented before, because was being heating and then immediately cooling the water, you'll incur a different scenario than the tempering. First things first, the rapidly cooling process, known as quenching effectively, lock on the structure of the aluminum and the elevate temperature. This can lead to a state of increased hardness and reduce malleable compared to heating only sample. Like reduce the malleability, like we can see here is hard here to malleable than the reference that actually we can like malleable like a little more. And when at tempering, to make a hole in this quenching aluminum, you might find that the metal is more resistant to the reforms. Like it's more resistant here. It's actually more hard. The hardness requirement is less likely to bend or stretch, and the sharp object might have a hardness tightening in the surface. That's the reasons why we can find like a hole here after the sharp one. I have a hypothesis for this one, and it's actually when the hot aluminum comes into contact with the cold water, rapidly cooling occurs and freezes the crystal structure in the current stage. Like the difference between here is that when we add cold water here, like they make like a stop, and here is like there doesn't happen anything actually. And this can generate internal stress in the material due to the different contracts and the rapid formation of this structure. As a result of the aluminum can harness by a tempering could have a more compact structure and higher mechanical strength compared to the anneal or slowly heated sample. That's the reason why we can find here that it's more resistant, it's more stronger. Like when we're trying to chop here, we can find that it's actually not going to happen. Actually, it's the hole here still. So yeah, those are my conclusion, and I think in summary, the thermal treatment of aluminum samples significantly affects their microstructural and mechanical properties. The initial anneal sample is more malleable but less resistance than here. While the temporary sample who have the higher stress and hardness due to alterity and its crystalline structure through rapid cooling.